Hello everybody, this is Jeff Jenness again. We're going to continue our discussion of GIS data types. So far we've discussed workspaces and we've discussed vector data, and so now we're going to pick up with raster data. Recall there's two broad categories of spatial data, and 90% of the time you're going to be dealing with either vector or raster. So now let's discuss raster. Raster is really pretty cool. The difference is it's composed of square pixels that completely cover a region, and occasionally these pixels are rectangular, but that's really rare. In most cases, your raster is going to have square pixels. I'll show you a picture of that in a second. Each pixel has a value, and all pixel values are actually numeric, but sometimes we interpret them as colors. They represent a general value within the pixel area. Now, raster data in general, they are not nearly as precisely defined as vector data, nor should they be understood that way. Pixel value is just a general descriptor of the cell. It's not the value at any exact location. So here's a typical raster. And clearly this is imagery, and not most, but many rasters are image data sets. In fact, any image file can be considered to be a raster data set. You may have noticed as you zoom into images, you see this pixelation effect, and well, those are the pixels. So in this case, we're looking at some imagery off the coast of California, a parking lot there on the beach. As we zoom in, we see the pixels, and we're zooming in a little car there. Now, I want to point out here that raster data, I said they're images, but one important factor is that they have spatial information so we know where they lay on the landscape. Now, notice the pixel size there. Pixel size is referred to as the raster resolution, and we care a lot about raster resolution. In fact, we often refer to rasters with the resolution in the name. We might refer to an image as a 10-meter pixel image, or a 30-meter pixel, or a 1-meter pixel. This means the size of the cell on the ground. Now in this case, I'm looking at a car there. I don't know exactly, but I'm estimating that those pixels are roughly 1 foot on the side. So we would call this a 1 foot resolution raster. Notice also in this image that these pixels, each pixel has a solid color in there, but the pixel is only kind of a rough estimate of what the value is at that location. This goes back to what I said about the difference between vector and raster data based on precision. Vector data is highly, highly precise. Raster data is only a rough estimate of the value within each pixel. And the value of that pixel should not be understood to be the exact value at any point on the landscape. Just because one pixel looks sort of whitish, that doesn't mean that the landscape is truly that color at any exact point. It's not like this is the value at the center of that cell or the upper left corner. It's just a rough estimate of the value within that cell. This means that you can't understand these rasters to be exact values anywhere. That's just an important basic understanding of rasters that you need to keep in mind as you analyze them. Now let's consider more about raster resolution. We care a lot about raster resolution because that gives us a sense of how precisely we are understanding the landscape. If we have a raster of elevation values, and that raster is, say, a 90-meter elevation, 90-meter resolution raster, that means we have an elevation value every 90 meters across the landscape. On the other hand, if we have a 1-meter resolution elevation raster, then we have elevation values every meter. So the second case gives us much more detail of the landscape, and this is something we care about. Now this slide, I want to show you that just because we know a particular resolution, it implies higher precision or lower precision, but we can't always rely on that. This is an actual example of a DEM, a digital elevation model, where somebody was concerned because they had the image on the left, and it just didn't seem to have as much detail of the landscape as they were expecting. The image on the right is the same area, and it has the exact same resolution, but the image on the right clearly has much more detail of the landscape. So both of these have the same resolution, but you can tell that the one on the left just was resampled likely from a coarser resolution raster, and so you didn't get all the data that you thought you got. Now, so just a word of warning. In the best case, the image on the left would have something in the metadata telling you where or how you created that DEM in the first place. The metadata doesn't always have that information. Okay, moving on. Let's talk about raster file types. You get a raster data set. What's the format going to be? ArcGIS recognizes lots of raster file formats, including all the standard ones, your JPEGs, your GIFs, your PNGs, TIFF files. All of these are normal images. You can take them with your camera, but they also serve as spatial data sets. Now, some image files have spatial information that are written right into the file itself. This Imagine format, Mr. SID, you might have heard of GeoTIFF. These have spatial coordinates and spatial reference information written right into the file. Not all of them do, though. JPEGs, GIFs, PNGs, these don't have any way to store spatial information, and so they have spatial information in a separate file called a world file. So what is a world file? If you're there's just a separate file with the same name, but usually has a W appended to the end of it. So if your image is flagstaff.tiff, then the world file is going to be named flagstaff.tfw. And so this is what the world file would look like. They're standard, very basic text files. You can open them in any text editor. And the numbers in the file just tell you how to position the image on the landscape. So what do these numbers mean? Oh, yeah, not all rasters use world files. Like I said, some have spatial information written right in, but if it doesn't, then this is the best you can do. So this is what those numbers mean. Pixel width, pixel height, the coordinates of the upper left corner of the map. Notice that all this is a set of instructions on how to place the image onto the landscape. It doesn't actually tell you what coordinate system it's in, and so it doesn't tell you if it's, say, UTM or geographic coordinates. So it's pretty coarse, but it serves the purpose. It places it on the landscape okay. Now you can make world files if you want. In ArcMap, you can make a pretty map, and then you can export it to a JPEG or a TIFF file or whatever. If you like, you can write a world file as you create the image. And that means that not only is it a pretty map, but somebody can actually load it into GIS software and see where it lays on the landscape. When you do this, you have to do it from the data view. If you're unfamiliar with data versus layout view, go back to take a look at the first lesson on Introduction to ArcGIS. That'll go over that. So if you want to export an image, just export a pretty map with a world file, then do it from the data view. Now there is one exception to this. If you're exporting your layout into a PDF, PDF does give you the option to add, it's not a world file, but it gives you the option to add spatial reference information into it. But otherwise, if you want to export just a JPEG, you're going to have to export from the data view, and you can add a world file if you want. Okay, moving on from that. All rasters are composed of either a single or multiple bands. So a raster is just a container for raster bands. Sometimes there's only a single band, sometimes there's lots. Image files usually have at least 3 raster bands, and each band represents a different electromagnetic wavelength. Now this is important. Most true color satellite and aerial images, they're not really true color at all. They look like true color, but most commonly they are a composite of 3 separate images. And one image shows the reflectance of the landscape in the red wavelength. So it's not showing the color red, it's just showing how the landscape reflects at that particular wavelength. One shows the reflectance at green, one at blue. You put those 3 into ArcGIS and you plug them into the red, green, and blue color guns or channels, then it shows up as what looks like a true color image. If this doesn't make sense, I don't know if any of you have ever looked really closely at a computer monitor. I mean, close like you have to use a strong magnifying glass. If you ever do that, you'll notice that each little pixel on your monitor is actually composed of 3 colors. It's composed of red, green, and blue. And that pixel shows red, green, and blue, each one of those at slightly different strengths. And from when you move back a foot away from the monitor, it all sort of blurs and gives the illusion of true color. True, more than just red, green, and blue. But truly, your monitor is only showing you 3 colors. All right, so one important point here is that you may have images taken at the red, green, and blue wavelengths, but you can plug them into any channel you want. You could take the red one and plug it into the green channel if you want, and vice versa. Or you could take colors that are completely outside of the visible range and plug them in as well. And we do this quite often, and we can get some really cool information from a raster doing it that way. Right, so here's the full electromagnetic spectrum, going in this case just from AM radio waves at roughly 1 kilometer frequency all the way to gamma rays. The visible range is just a small part of that full spectrum. And when we do this multispectral imagery, each image just shows the reflectance at some narrow slice of the total spectrum. And when we're doing this imagery that looks like true color, we're taking slices here at the red, green, and blue sections of the visible range. So in this case, imagine that we've taken 3 images. One in the band 1 is in the red, band 2 is in the green, band 3 is in the blue. We take those 3 images, we plug them into ArcMap, we plug band 1 into red, band 2 into green, and band 3 into blue, just like we see here in this sample. And it looks like a true color image. It looks as if we were actually in an airplane looking down and seeing the landscape. Now, one important difference here from reality is that there could be something down on the landscape that is it's within the visible range, but it could be at some other part of the spectrum here. It could be in between band 1 and band 2, maybe in that yellowish range. It could be shining like the sun. It could be blinding us if we're in our airplane looking down, but we wouldn't even see it in this image because this image is only taken those 3 slices of the spectrum. Those 3 slices don't happen to include that bright spot. So just keep that in mind. Now, we don't have to view all 3 at the same time. We could just take a single slice of the spectrum, and in this case, when we take a single slice, we usually show it in black and white. Obviously, it doesn't mean it's black and white on the landscape, but light color means that it reflects at that frequency. A dark color means it absorbs at that frequency. So in this case, we're looking at this slice in the red band. This means this is how the landscape reflects in the red wavelength. Now, a little bit more. Most satellite and aerial imagery, they have more than just the 3 red, green, and blue slices of the spectrum. Many of them show a lot of wavelengths outside of the visible spectrum. And these are really useful for a lot of ecological applications. One example, Landsat Enhanced Thematic Mapper has 7 bands. 3 of them are in the red, green, and blue slices that we use to make natural color images, but there's 4 more that offer in the infrared range. And these are useful for things like vegetation health. So here there's Landsat showing Flagstaff area. We're taking bands 1, 2, and 3, which correspond with blue, green, and red. If we plug them into the correct channels in ArcMap, it looks like a true color image. This sort of looks like Flagstaff would look like if you're in a plane high over the landscape. But we can shift them out. We can pop in an infrared band, and all of a sudden the landscape looks different. So one important thing about this is that certain vegetation characteristics really stand out in the infrared range. Chlorophyll, for example, reflects differently in the infrared than it does in the visible range, and you can take advantage of that. And in fact, let me show you a demonstration of how this works. Okay, this here is a Landsat image of the Grand Canyon. This is an image that's actually in your data file, so if you want to load it up, you can. It's in the additional data folder. It's called Landsat_gc.tif. It is an 8-band raster because it comes from Landsat Enhanced Thematic Mapper. Remember, it has 7 bands and represent different slices of spectrum, and then an 8th band that sort of covers the whole range and is useful for making it look a little sharper. All right, now notice that this is how it looks when you first load it up. You just load up the raster itself. You see that band 1 is going into red, band 2 is going into green, and band 3 is going into blue. Now here, this is your actual lab exercise document, lab exercise 5. It's one where you get to play with this particular raster. Notice that band 1 in Landsat corresponds with this particular wavelength. That puts band 1 right in this range. Band 2, 0.52 to 0.6, goes in this range, and band 3 goes into the red range. So band 1 should be blue, band 2 should be green, band 3 should be red. When you load it into ArcMap, band 1 is red, band 2 is green, band 3 is... So they've got band 1 and band 3 mixed up. So let's fix that. You just double-click on the layer to open up the layer properties. Go to Symbology, red, green, and blue. Right now they're set to red band 1. We're going to fix that, so red should be band 3. Blue range should be band 1. So now it's fixed. We hit OK. And there we go. Now it looks right. This is more what the landscape would look like staring at your plane looking down. A couple things to notice. Why is this white up here? Hopefully you all are saying that's because that's snow, and it's true. But the question is, why is snow white? Well, if you think about it, that is because snow reflects. Snow reflects light. We've noticed that when we're out there in the snow, and it's blinding sometimes. But the key point here is that it reflects in the visible range. What does snow look like outside of the visible range? Come back over here. We notice that we have several bands, band 4 through 7, occur outside the visible range. They're off in this area here. And so these are in the infrared bands. Well, we have band 4, 5, 6, and 7 available to us. What does it look like in that range? Band 4, this is in the near infrared, still sort of whitish up here, so it's reflecting. Snow reflects at band 4. Snow starts to absorb the wavelength when you get in band 5, and band 6, and band 7. So this means that if your eyes perceived in that infrared band, snow would look black. It would look like a field of coal, which I think is really interesting. So this is a simple example of what snow does. Snow absorbs in infrared. Let's look at some of the visible range, and it reflects very well in the visible range. Now, that's great for snow, but it has further implications when it comes to vegetation. So we can zoom in. I'm going to zoom into this area down here. We're curious about this area right here. If we look at it in the true color format, we can see sort of that there's something going on here. It looks like vegetation outside of it. Something's happening in here and something's happening over here. Probably just the consequence of different management strategies. Suppose we want to capture this area. Suppose we want to easily identify this. In the visible range, we can kind of see it. Suppose the visible range isn't quite the best place to capture that. Maybe we can check different wavelength and see where this area seems to reflect the most. We can try different wavelengths to see what wavelength seems to show this area the best. Okay, let's look at that. Let's just look at them one by one. This is one wavelength. Not really seeing it stand out there. Let's another visible range. It stands out a little more. Band 3 is also in the visible range. It stands out a little bit. Let's go into the infrared. Band 4 doesn't work for us. I can't tell anything's happening there. Band 5. Band 5, it's starting to stand out. Deeper in the infrared, this is really starting to glow. So we go into the infrared range, then whatever is happening on this point of the landscape is just really distinctive in this wavelength. All right, so here we see we might want to step into some of these infrared bands to be able to better distinguish important phenomena on the landscape. Just a quick tangent here on raster bands. I like looking at this one because I think it's just a fun image. Up till now, we've been discussing raster bands in terms of each band being a different slice of the electromagnetic spectrum, but you don't have to use images in the bands. This particular thing you're seeing here is a multi-band raster image where I have one band as elevation, one band as slope, and one as aspect. Have elevation plugged into the red channel, slope plugged into green, and aspect plugged into blue, and this is the kind of thing you get. So you can play with this stuff. It's just sort of fun. All right, moving on back to imagery topics. Multispectral imagery. This is the name for multi-band rasters where each band represents a different slice of the spectrum. Now, Landsat Enhanced Thematic Mapper is one popular one. There's a newer version of Landsat out now, and then there's several other flavors out there. Some have the same bands as Landsat, some have a lot more. In fact, once you get images that have lots and lots of bands, there are some systems out there that have thousands of slices of the spectrum for every image. Then we stop calling it multispectral, and we start calling it hyperspectral. And there's a lot of interesting research these days into how to identify specific phenomena on the landscape based on some combination of spectral bands. Some pretty cool statistical analysis, multivariate stats, taking any number of bands and pulling out signatures of these things that we care about. So it's pretty neat. There's a couple of real simple examples. One, you might have heard of NDVI. That's the Normalized Difference Vegetation Index. It just uses two bands, one in the near infrared and one in the red slice of the spectrum. And based on this simple mathematical equation, you can pull out chlorophyll reflectivity. So chlorophyll reflects differently in the near infrared than it does in the red, and you can take advantage of this great difference to pull out cases of lots of chlorophyll. And this sort of corresponds with vegetation health. A very closely related one is the Normalized Difference Water Index. Just switch out the red with the green band, and all of a sudden you get something that shows where water is reflecting on the landscape. This is kind of a neat way to find streams and ponds on the landscape. These spots with water just shine really brightly when you do it this way. Okay, now some cool imagery trivia. We've been discussing this in the context of aerial and satellite photography up to now, but satellite and aerial photography are not the first systems to use this multispectral method to create color images. Some of the very first color photographs ever taken use this method, and they did this by taking several images of an object and using colored filters for each image. So, for example, here's a color photograph taken in 1877, long before there was color film. So it's not a great image, but it is a color image from 150 years ago. So you can tell the red, you can tell the vegetation. You can look closely at the corners here, and you can see how there's actually multiple images stacked on top of each other. So what they did here was they took one image with a red filter over the lens, another image with a green filter, and another image with a blue filter. And then they would, in order to view it, they couldn't print this in color. In order to view it as a color image, they would set up 3 projectors in a room. One projector would show the image taken in the red slice of the spectrum, and that would have a red filter over it, so it would be projecting up in a red color. Then you'd do the same with the green and the blue, and you'd look up on the screen, you'd see this color image, which is pretty clever. Here's another example. The colors here are just really amazing to me. This is Russia in 1910. There's a whole series of these images taken in Russia before the First World War, before the Revolution, and long before there was color film available. I think this is really interesting. Okay, so we've been discussing rasters so far as images mostly. Now, there are a whole broad category of rasters that have nothing to do with imagery, but they just describe the landscape and various metrics, and so we just call these numeric rasters. So rasters don't have to show imagery. You can describe the landscape in any number of ways. One of the most common is just by elevation, where every pixel has the elevation within that area. They call this a digital elevation model, or DEM. Sometimes they call it a DTM for digital terrain model. Now, other examples are slope, aspect, curvature, surface area. All of these are numeric descriptors of the landscape. You can have hydrologic functions like stream flow, flow direction, contributing area. You can have habitat quality. We often call habitat quality models, we call them habitat suitability models. Now, here's a simple example of a DEM. So it's just elevation values for every pixel. You can sort of imagine it on a perspective. It looks like a bunch of columns rising up adjacent to each other. This should also help drive home the point that raster pixel values are not highly precise. You look at that central cell, it says it's 165 units high. Well, obviously the landscape isn't arranged in that stair-step pattern, so that 165 is just an estimate for the elevation within that region. Should not be interpreted as the exact elevation at any point within that cell. DEMs are fun to play with. You can turn them into slopes, curvature. Any shape of the landscape can be derived from a DEM. Something people don't always realize is you can use those same functions on other numeric rasters. So here I'm showing habitat quality. This is some habitat suitability model for some species. You look at that ridge through the middle. Well, that ridge is actually a riparian area because this particular species prefers riparian habitat. So the riparian shows up as relatively high on the landscape. Now, with a DEM, you could do things like calculate slope. Well, slope is the rate of change of elevation. So you can apply the slope algorithm to other rasters. In this case, we're getting the rate of change of habitat quality. So that can be informative. It can show us where on the landscape habitat quality changes quickly. So just keep this in mind. A lot of people don't know that you can do this. Okay, let's think about attribute data now. When we discussed feature classes, we talked about the fact that there's a geometric object and then there's attribute data associated with it. This lets you click on it in ArcGIS, and you can click on a stream and you can see the attributes that are associated with it, the stream name, the flow value. Click on a trail, you find out the trail name. And this is good information. Well, some rasters also have attribute data. Not all rasters do, but some do. And the actual cell values of all rasters are numeric, and that means that there may be interesting information on the raster, but it's not written into the cell. So maybe you have a raster of, say, cover type, vegetation type. Well, the cell value is always going to be a number, but we can consider that as a code value that corresponds with some other value. Value of 1 means ponderosa pine, a value of 2 means mixed conifer, something like that. Well, if we can write those equivalent vegetation types into the raster itself, then they have to be written into a table. So the cell value would have a value of 1, but the attribute table would tell you that 1 means ponderosa pine. Now, if a raster has an attribute table, then it's going to have a separate attribute table for each raster band. And if the raster cell values are decimal values, meaning they're not integer, then this raster is probably not going to have an attribute table. If a raster has integer values, though, then the raster probably will have an attribute table. And remember that raster attributes are associated with cell values, not cells. This makes them, and here I'm using cell as the same thing as a pixel. Now, this is different than feature class attributes. Remember that a feature class attribute corresponds with a specific geometry. The raster attributes, they correspond with the cell value. So that cell value can exist anywhere on the landscape, and they all are associated with the same attribute values. So for example, here's a veg type raster like I was discussing earlier. If you just look at the cell values, look there, the vegetation type ranges from 11 to 2549. Well, that's great to know, but it doesn't really tell us what we need to know when we're curious about vegetation type. Fortunately, this particular raster does have an attribute table, and here we see where each cell value corresponds with a particular vegetation type. If it's a value of 11, it means open water. We can take advantage of these attribute values when we map the data, so we can symbolize our veg type raster by one of those vegetation values. So in this case, I'm symbolizing it by this class called NVCS class. This data set, by the way, is from Landfire data, and Landfire is really cool. It classifies the landscape in several vegetation systems. And so there's some Landfire data for you to play with in one of the labs, at least sometime in the semester. Okay, and that's what I have to say about raster data. So far we have discussed workspaces, then we've discussed vector data, and now we've just discussed raster data. And so the next section will discuss various other types of spatial data. They're less common, but I think you'll be interested to see what they are. All right, thanks so much.